In the last two lessons, we looked at approaches to playing small games. That is, games for which there is sufficient time for a complete search of the game tree. Unfortunately, most games are not so small, and complete search is usually impractical. In this lesson, we look at a variety of techniques for incomplete search. We begin with simple depth-limited search, and after that we turn to two variations. First, fixed depth heuristic search, and then variable depth heuristic search. And in the next lesson, we examine statistical methods for dealing with incomplete search. Simplest way of dealing with games for which there's too little time to search the entire game tree is to limit the search in some way. In depth-limited search, the player explores the game tree to a given depth. A legal player is a special case of depth-limited search, in fact, as is a random player, where the depth is effectively 0. The implementation of depth-limited search is a small variation on the implementation of the minimax player described in the preceding lesson. The only difference is the addition of a level parameter to max score and min score. The parameter is incremented in min score on each recursive call to max score, as we see here at the bottom. And if the level of any particular non-terminal state in the game tree exceeds a predetermined depth limit, rather than expanding, max score simply returns 0 for that state, which is a quite conservative lower bound on the utility of the state. Here's an example of depth-limited search. By limiting the depth, the player does not need to explore the entire tree, yet is still able to find a solution that nets it 80 points. Not as good as 100 points that it might get if it were able to go deeper into the tree, but it's better than 50 and a lot better than 0. The most obvious problem with depth-limited search is the conservative estimate of 0 for non-terminal states is really not very informative. In the worst case, none of the states at the given depth may be terminal, in which case the search provides no real value. It just gets 0 everywhere. And we're going to discuss some ways of dealing with this problem in the next segment, and again in the next lesson. There's also the opposite problem. The depth may be set at too great a level, forcing the player to search deep into the tree before finding an answer that exists at a shallow level. Now, this problem is serious if along the way the player runs out of time before encountering the shallow solution. One solution to this problem is to use breadth-first search rather than depth-first search. We start off at the root, and we expand one level, checking each node for termination. Then if we halt if we ever encounter a terminal state with sufficiently large value. And if time expires before this happens, we simply choose a branch that leads to a node with highest terminal value. Breadth-first search has the merit that it finds the shortest path to a maximal goal. It has the disadvantage that it consumes space that's proportional to the size of the expanded game tree, which can be exponential in depth. Using this approach, in some cases, the player can run out of memory and crash. An alternative solution to the problem is to use what's called iterative deepening, exploring the entire game tree repeatedly at increasing depths until time runs out. We search the tree to depth 1, then we search the entire tree to depth 2, then we search it again to depth 3, and so forth, using depth-limited search on each of these iterations. The primary disadvantage of this approach is that it requires space. Primary advantage, of this approach is it requires space that's linear in the depth of the explored portion of the tree. The entire subtree does not need to be stored, yet it still finds the shortest path to an optimal solution. And the primary disadvantage is that portions of the tree may be explored multiple times. However, as usual with iterative deepening, this waste is usually bounded by a small constant factor. Now, why is that? The size of the fringe of the tree is approximately the same as the size of the tree above the fringe. So searching the entire tree in additional time requires only the same amount of time as you would need to expend to explore the fringe to another level anyway. This means there is extra work, but it's bounded by a simple constant factor, like a factor 2 or 3.